Okay, so here is a circle. This is going to be the chassis of the car. I'm going to put on two wheels, and this is going to be a top view of the car. Let's just put two wheels. Okay, so what is done in this car is those wheels are, well, these are circular wheels, obviously. They are connected to a motor. So you can spin it at whatever speed you want. And how do you make a car with just two wheels? Well, what you do is in the front, you put a caster. Okay, the reason why you need a caster is because it's just difficult to keep something upright with just two wheels, right? You need at least a tripod. So you put a caster. Hey, do you know what a caster is? So, okay, so we don't have a, do we have a, any of these chairs have caster? I don't think any of them have casters. But if you go to, let's say, a big box store, let's say Walmart, you look at the front wheels of a cart, it'll basically be a caster. So the caster is such that the way it works is if you push in some direction the cart, it'll actually go in that direction because the casters take the direction which you push the particular car. So the caster actually acts like a mechanism to just go with the flow. So if the car wants to go left, it'll actually let it go in the on the left side. You could replace the caster with like a sliding, like a rubber pad, which would be absolutely fine. It would serve the same purpose, except that if you put a rubber pad in the front, it'll have more friction compared to a caster, which is a wheel. And that's why you don't want to waste energy putting a rubber pad. But it's absolutely fine if you want to just put like a rubber pad down. Okay, so search for caster, or look when you go to a shopping store, big box store, look at the front wheel of a cart. Or if you go to a place like IKEA, they actually have casters on all four wheels, so you can actually go in any direction. It's much smoother to use that cart than to use the one which is in Target or Walmart. Okay, so that's my robot top view. Let's put in an axis. Okay, I always like to choose the x-axis to line along the caster, and then I'll choose a y0 to the left. And it's done in such a way that if you use your right hand and you go from x cross y, you curl your fingers from x cross y, your thumb points in the z direction, right? And that z direction points out of the plane of the paper. So assuming that the caster is always in front, the rectangle I drew there on the right side is the right wheel, and the rectangle I drew on the left side is the left wheel. Okay, we're going to assume that we can spin the right wheel the way we want. So let's define the velocity to be phi dot r, and the left wheel velocity is phi dot l. Okay, so how do you make this move? I hinted at this earlier. If you want this differential drive, if you want it to move straight, all you have to do is make phi dot r equals phi dot l. So if they're moving at the same speed, it'll go straight. If you want to turn right, okay, how do you turn right? Well, it's clear that the right wheel, left wheel, has to turn faster than the right wheel, right? If this wheel spins faster than the wheel on the right, then it's going to turn this way. So if you turn right, then the left wheel has to turn or spin faster than the right wheel. And if you want to turn left, the right wheel has to turn faster than the left wheel. Okay, so I'm going to start the car in this position such that x-axis is horizontal, y-axis is vertical. Let's call this point C. And let's say that we spin the wheels and the car drives around and it lands in a different position. So now in this position, the wheels are like this. X1, Y1. It's the same point C, but it's in a new frame. So let's call this O1. Okay, so let's put a few things. I would need this in my derivation. I'm going to assume that the radius of the wheel is R. I'm going to assume that B is half width between the two wheels. So the distance between the two wheels is 2B, but B is the distance between the midway point and the wheel. And then let's give this point a name. Well, coordinate XC, YC, but we're interested in frame 0. And this point here is going to be XC1, YC1. As a result of moving around, the orientation of the caster with respect to the x-axis is now theta, right? It started with theta 0, and it's theta. Okay, remember, we can spin this wheel at phi dot r, and we can spin this one at phi dot l. Okay, so what we have on the left is position at time t equals 0. And then what we have on the right top is position at some time t1. Okay. So here's the problem setup. What we want to do here is we want to be able to describe the movement of the car, and it's good enough to describe the movement of uh, the center C. Okay, so we want to compute x dot C, y dot C in frame 0. So here's the difference between this and a manipulator. In a manipulator, you could actually compute the positions. In this case, it turns out you cannot compute the positions. You need to compute the velocities and integrate the positions to get the, integrate the velocities to get the position. This is actually what is known as a non-holonomic system. So a non-holonomic system is a system which cannot be integrated. Okay, and then that only gives you the position of C. We also need to know where exactly it's heading. So we also need a formula for theta dot. So here's the car with at some orientation. Sorry, x1, y1. O1. Okay, and then remember that the speed of the left motor is phi dot L, and speed of the right motor is phi dot R. Okay, so we'll we'll try to compute these things. Okay, so before we do that, instead, let's try to compute x dot c1 and y dot c1. Once we do that, because we've run this figure, it's easy to find what is xc dot 0, yc dot 0 through the rotation matrix. Okay, so what we'll do is, let's assume that phi dot L equals 0, phi dot R is not equal to 0. So what's the consequence of just spinning the right wheel? Okay, so I'm going to draw this figure slightly differently. I'm just going to show the point connecting the two wheels. So let's say this is the left, this is the right. And since we hold this at 0 speed, phi dot L equals 0, and this one is spinning, so what will happen is this will sweep an arc. So it will be an arc. Right, that's kind of obvious. Now, what we try to do is we'll try to compute what is this distance, what's the distance traveled in a short amount of time, a really short amount of time, delta t. Yeah.
So are we assuming that's a triangle and not curved?
It is curved. It is curved. Absolutely, it's curved. It's short amount of time, it will become a triangle. So we are trying to assume, well, we're going to, I've blown it up, so it's actually a curve, but for the purpose of calculation, we'll assume it's a small time, so we can replace the arc with a straight line, so it becomes a triangle. So that's what it'll come. We'll get to that. Okay, so we know that phi dot. So this distance. Now, if you remember this, if you have like a circle, and then there's a radius, then this. So let's say that this angle is phi. Then we know that this arc length is r times phi. Okay, and the rate of change of this would be, since r doesn't change, we have r phi dot. So this distance covered here is r phi dot. Okay, so it's still an arc, right? We've not made the triangle approximation here. It's still an arc. It's r times r times phi. Right. So we are interested not in the movement of the right wheel. Let's just call that R and L, just easy to keep track of it that way. Okay, but we're interested in the motion of point C, which is this one. So since we assume that C is midway between L and R, the distance covered here by this point C in the same time would be R P divided by 2, right? Just by construction. So this is where we, this is also an arc. So we still have the arc assumption, but now is where we do the triangle approximation. We say that the distance covered along x c, and remember that this is the x1 frame. So x c1 is r p divided 2, and this is where we actually do the triangle assumption. So far, till r phi, we did not do the triangle assumption. So why we do that? Well, if it was going in an arc, then it'll not only move in the x direction, but there'll be slight movement in the y direction, right? Because it's an arc, right? But when we make the straight line approximation, we assume that the motion is only along the x-axis and not in the y direction. Okay, so that's the triangle assumption here. Okay, it's true to an extent, provided. So this is what I have there is a bad approximation because xc equals r phi. But then if you take the rate of change of this, it's much more accurate because now we are looking at a really small segment, r phi dot. So this is taking the expression here for, so let me just write it here, xc is r phi 1 is r phi divided by 2, and then take the derivative. Okay, so that's that. We see that y dot c1, okay, that is the movement along the y direction or y1 direction is clearly 0. Okay, so it cannot move in the sideways direction. Okay, that's why you cannot, it's really hard to parallel park. If you could do, if y dot c could be achieved, then you could just move it to the side. So there are certain kind of wheels which allow you to do sideways motion. They're called omnidirectional wheels. There are like rollers on the wheels which allow you to move in the lateral direction. Okay, so what we did here can be done for the other way. So we assume that phi dot r equals 0, phi dot l is not equal to 0. So we're doing the same kind of thing. Now keep r as 0, not move the right wheel, but move the left wheel. So what will happen as a consequence is if r is fixed, l is moving, it'll also do a similar thing. It'll be an arc. C will be an arc. It'll also be xc1 would be, so I should have, my bad, I should have put phi r, right? So this should be phi r. And so if I have the left wheel moving, it'll be r phi l divided by 2. This is L. So the same thing will hold. X dot c1 is r p dot l divided by 2, and yc doesn't change. So yc dot is still equal to 0. Okay, so what I need to do is I need to take these two and then put them together, because since it's linear, you can just add the two and then you'll get the result of allowing both the wheels to spin. So sure. Yeah, so just we put it together. If phi dot L is not equal to 0 and phi dot R is not equal to 0, then X dot C in frame 1 is going to be R divided by 2 phi dot R plus phi dot L, and then YC dot 1 equal be just 0. Okay, the car can move straight, cannot go sideways. So it's interesting that in that frame, the frame 1, I'm just going to go back a little bit, the car can only move in the straight direction, cannot move in the sideways direction, right? Which makes sense. Okay, so we have that. Okay, so we as I said, we are trying to get everything in base frame 0. So what we'll do is we'll use an equation we've written down earlier. If we know the position of point C, C being the point midway between the two wheels in frame 0 is R10C1, right? This came from our rotation derivation sometime back. So what's C0? It's basically X C0, Y C0 equals, let me just write it as R10, X C1, Y C1. Okay, what we'll do is take the derivative with respect to time. Okay, and then you should always, well, you need to do the, it's chain rule, right? So you need to do derivative of r. Okay, now here's the thing, which is our calculation or derivation was under the assumption that we are looking at straight line motion. We have to do the curving motion later on, but for this derivation, we're just doing the straight line motion. So this part is 0. There is no rotation. Okay, there is rotation in general, but for this derivation, we did not consider it because we're looking at straight line motion, only movement in the translation direction x, c, y, c. So the formula for the translation motion is going to be, I'm going to expand out r10, it's cosine theta minus sine theta, sine theta, cosine theta. Okay, now we have already computed what xc1 dot and yc1 dot is. So we can sub that in. R divided by 2 phi dot L plus phi dot R and then 0. Okay, so x dot c0 okay, so it comes out to be R divided by 2 phi dot L plus phi dot R cosine theta, and then R divided by 2 phi dot L plus phi dot R sine theta. Okay, so this is just one part of the, we still have to compute what phi dot is, theta dot is, sorry. So this is just telling you how the robot will translate if you're given the speeds and then if you're given the orientation. Okay, now let's look at the second part, which is what is theta, which is the rotation of the robot. So next is, so we are computing x dot c dot. Now we'll compute theta dot. Here we compute theta dot. Okay, so we do a similar thing, which is assume phi dot L equal to 0 and phi dot R is not equal to 0. So when that happens, we have we have L, R is going to spin, and this is just exaggerated, right? So okay, so we saw that this arc length is R P dot R. Okay, so everything remains the same. It's the same. So it's r times phi dot. Okay, so that's the r trace. Now what we have to do here is the following. We need to somehow so this angle is theta. So if you, well, let me just go it this way. So there's a wheel. This is the wheel. And it's going to, before I, so this is just to complete this. This is basically r phi r, right? That is the same thing we wrote down earlier, just to make it complete. Okay, so now we have that. Now we assume that this was the distance between the center and one of the wheels was b. So this total distance, the width uh, of the chassis, that is the distance between the wheels, is 2b. Okay, and we have the angle here is theta. That's the arc swept by the point r when it is spinning by phi r. Now what we can do is we can try to relate, we can see from this particular calculation, or the way, this way of thinking about the arc length, that r phi r, which is this, is the same as 2b times, so 2b is now going to be the radius. Theta would also give you the same thing, the arc length, right? This is the two ways of calculating. Is one way is we look at the arc due to a radius of 2b. So 2b times theta will give the arc length. Another way of thinking of it is a wheel, and that wheel is spinning by an angle of phi r. A consequence of this, the arc length traced by the wheel is going to be r times phi. If things don't slip, if the wheel doesn't slip, r phi should be equal to 2b theta, or theta should be r divided by 2b times phi r. Okay, or since we're interested in the rate of change of theta, theta dot will be r divided by 2b phi dot r. Okay, so this is the angle theta turned, or rate of change of angle theta turned, is given by this formula. But this is only when one of the motors, that is the right motor, is spinning and the left motor is fixed. We could reverse the logic and say, assume that phi dot r is equal to 0 and phi dot l is not equal to 0. In this case, let me just draw the figure, but you get a similar derivation with a negative sign. So let's do it the other way. It will be r phi dot l divided by 2, sorry, r dot phi. Phi l, this is the arc length, and then since this is 2b, this angle is now going to be minus theta, because it's spinning in the clockwise direction. Clockwise direction is negative. So we have, with the same reasoning, r phi dot l equals 2b times minus theta. So r phi, and then theta is minus r divided by 2b phi l, and then the formula is phi dot equals minus r divided by 2b phi dot l. Okay, so this is the angle turned or rate of change of the angle due to the left motor spinning and right motor fixed. And because all this calculation was a linear, everything is linear, you can add the two, so sort of superposition. So now if theta dot r is not equal to 0 and theta dot L is not equal to 0, then theta dot, you just sum the two, will be R divided by 2B P dot R minus P dot L. So we've sort of completed the derivation of all the three things we're interested in. How much does the car move in the XY direction, and how much does it rotate? Okay, now there's a way to simplify this a little bit that will actually help us. So you see this formula, we have this term, right? And then if you look at the previous one, which is here, you have this term. So what people do is, just to make it sort of compact, they just let me just write it down. Say they define a new variable. Let me call that the velocity or linear velocity. Just let's put 1 here and then 2 here. So to make things compact, what we'll do is we'll assume that velocity is given by this formula. 0.5 r times P dot r plus P dot L, and then omega is 0.5 r divided by B P dot r minus P dot L. Okay, and so consequence of writing it this way, you can now write the equations as V cosine theta, phi dot C0 is V sine theta, and theta dot is simply omega. So you will see if you happen to read any books, you'll see that they'll write the equations of a differential drive car like so, but really V is a variable which tells you how much you are going to move in the forward direction when it's the average of you can think of that as an average of the speeds of the right and left wheel times r, and then the omega is basically the difference between the speeds divided by it. And it makes sense because omega gives you how much you will turn and V gives you how much you'll move forward. Okay, so that's the standard equations you see if you come across a differential drive car. Okay, so we have that. Now we said our goal is really to track the car in future time. So if you want to do that, you need to compute xc, yc, and theta. So what you can do is you can use if you remember, if you took numerical methods, there's a method called there's something called ordinary differential equations. Okay, you might have also seen ordinary differential equations in maybe a math class. So you need, if you know where the car is at time t equals 0, you can then integrate the equations of motion, those three, and then get what happens at any instant of time. So one of the sort of popular method, not very accurate, but it's a good method, is called Euler's method, which takes these equations and then integrates it. So the Euler's method is what we'll use, and then there are other ways. And the one which people normally use is called a Runge-Kutta, but let's just use the Euler's method. So the next step is compute xc, yc, and theta given the history of V, so V of t and omega of t. So you spin the motors at different speeds, so you sort of know the history, and so you're told to now compute what xc, yc, and theta is. So the formula is the Euler method will give you xc at time t plus delta t as xc at time t plus a step size, and I talk about the step size is velocity at t cosine of theta t yc at t plus delta t equals yc at time t plus h times v of t sine of theta t, and then theta at t plus delta t is theta at t plus h times omega of t. Okay, so h is known as the step size. It's typically a small value, for example, 0.001, so 1 millisecond. Okay, the smaller it is, the better is your calculation. The bigger it is, the more worse it is, but you can't make it too small, because if you make it too small, you'll be caught up by the machine accuracy. So you can't make it, for example, 1 in negative 15 doesn't make sense. It will not work well. And also it will be too slow, right? If you make it 1 in negative 5, it is a good value, but when you try to take 1 in negative 5 and integrate, your calculations will slow down. You also need to know xc 0 at time t equals 0, yc 0 at time equals 0, and theta at time t equals are known. You cannot do this calculation unless you know what happens at what is the position of the car at time t equals 0. So those are the other things. So if you know these things, then you can use the Euler's method to solve. Let me just put it down. It's called the Euler's method. So these things. This given, sorry, this is Euler's method. And then this is given. So what we'll do is we know the values at 0. You apply this formula, find what happens at t plus delta t. Actually, this should be t plus h. My bad. T plus h. And then you do, next step will be t plus 2h, 3h, so on. Okay, so I'll show you how to do this numerically. So here we'll compute x0, xh, x2h, so on till whatever time you want to go to. Similarly, y0, yh, y2h, and then theta 0, theta h, theta 2h, and so on. So I'll show you a code which will do this, which is basically given the time, given the velocity and omega history, will actually do the calculation x0, y0, theta 0, and so on. And once you have that, once you know position of the center, you know the orientation, you can actually make a plot and see how a car would move. Okay, but remember, you need to give it the velocity and linear and rotational velocity v and omega. Yeah, first, let me just run this code. So you'll see a circle representing the car. It goes straight down and then turns and then goes to the right. Okay, so the way I can do this is by specifying v and omega. So what I did was this. Let's see. First of all, it's about 90 lines code. There's clearly an animation function which will do the animation, which is probably the first thing we'll look at. It basically draws a circle of radius 0.1. This probably is explanatory. It basically gives the points on a circle, and then given the x position, y position, so it'll be xc, yc, and theta. It basically draws, it's a circle, and then the circle needs to translate and rotate. So what I did was I put the circle rotating, translating, but I also drew that line on the circle to just show the orientation. So I think that is done by using x and x2. So x2 is the one point on the circumference. I drew that point and then I just rotated it so that looks like the car is turning. And this is basically line robot shape. It basically should be self-explanatory. So this part of the code is about 30 lines. So 90 lines, so 60 lines are for the remaining part. Now there's Euler's method, which basically does the following: that same formula. Here x1 is the value of x at time t plus delta t, value of y at t plus delta t, theta at time t plus delta t. So it's just making the formula slightly short by splitting into two parts. One is I compute x dot c here and then sub it in, but there's a step size you can see. And then all this does is returns this for the loop is not here. It's basically just does one time step. So if you give it what has at this instant and you give it something about a history u, that is v and omega, it basically computes the x, y, and theta at the next time. And so once you have that, so that function, that's about 30 lines of code. So the main 30 lines, the last 30 lines basically does the actual main file, right? So I have to give initial configuration 0, 0. So I started the origin and with the orientation of 90. So it's pointing downwards. That minus pi divided by 2 means it's 90 degrees downward. It's pointing downwards. Edge is 0.1. I could have done it 0.01. It'll be more accurate, but it'll be slower. And then what I do is I have 3 segments for velocity. First, I just make it go at certain speed down. So that is t1. For next time t2, I make it just turn. I keep v 0 and then omega is non-zero, so it turns. And then for time t3, I get it to go straight again. And that's why you see it going straight, turning, and going to the right. Okay, so I specify, you can see 0, that's velocity is 1. Then I only make it spin at 90 by 1.57, and then I make it go straight 1. So then you put this all together, you do Euler integration, and there you have the car moving. So here is the animation goes straight, then only omega, and then go straight. Now you could do something interesting, which is you could also have it turning or moving straight. So you could keep I, 0 equals 5. So now you can see it's also turning as it's moving. So it's clearly going to track an arc, right?